So far we have discussed what is an electric dipole, what is electric dipole moment, what is the electric field at a particular point due to a dipole in case of axial as well as equatorial line. Now what we do is we place this dipole in a uniform electric field. Uniform electric field means the magnitude of the electric field at every point is the same. It is not changing. The electric field is not changing. It is uniform at every point. That is known as uniform electric field. And what we do is now we place a dipole inside that uniform electric field. This is my dipole inside a uniform electric field. The direction of the electric field is on this side. So this side becomes what? Positive. This side becomes negative. It is because the direction of the electric field is from the positive to the negative. Hence, what I do in such an electric field, I place a dipole like this. This red mark denotes the positive charge. This blue mark denotes the negative charge. So when I place the electric dipole in this way, since this is the negative side, this is the positive side. Okay, again I am repeating, the direction of the electric field is from the positive to the negative. Therefore, this side becomes negative, this side becomes positive. Now this is the positive side, this is the negative side, which is the positive charge and the negative charge. Now when I place this particular dipole in a uniform electric field in this way, then what happens is that there will be an attraction between the positive and the negative. This side is negative, therefore this will be attracted towards this side, and this side being negative, and since this is the positive end, therefore the negative is going to get attracted towards the positive, and in doing so a force is going to act at every point in this dipole. Therefore it experiences a force in this way. One force is going to act on this side and one force is going to act on this side. Therefore it experiences a force in this way and the movement of the dipole starts. Since the positive is going to get attracted towards negative and the negative is going to get attracted towards the positive, therefore it starts rotating. Okay, this is how it is going to behave when a dipole is placed in a uniform electric field. Now in this regard, what we do is we try to analyze the force acting upon this particular dipole and how the dipole is going to act in this type of situation. In this case, it is rotating. There is no linear motion involved. There are a couple of forces acting. Hence, this dipole is not going to have any net force. The net force in this case is going to be 0 because there is no linear motion. Hence, in this case, the net force is 0. Whereas it is going to experience a couple of forces. And when a couple of forces is going to act on a dipole, it is going to rotate. A torque is going to come into play, which is the net torque is going to come into play in case of circular motion. Because in this case of the dipole, it is not going to experience a linear motion. It is going to experience a circular motion. Hence, we take the torque into consideration. So torque in this case will be equal to F, which is the force, into area of the couple, which is the distance this from B to C. This is the distance. You can take it as F into the distance also. This particular symbol denotes tau. This symbol is known as tau. So tau will be equal to force into BC, this particular line, this particular distance. So tau will be equal to F into 2a sine theta. So in order to get this distance, what I do is I take the help of trigonometry, where sine theta, that is some people have perpendicular by hypotenuse. So I can replace BC as 2a sine theta. Since sine theta will be BC divided by 2a, therefore BC is going to be equal to twice a sine theta. So I substitute for this as twice a sine theta. Since we know that the formula of force in case of electric field is QE, therefore tau will be equal to QE into 2a sine of angle theta. We know that the electric dipole moment is twice AQ, therefore take this twice A and Q and make it as the electric dipole moment P. Therefore, your final equation for the torque experienced by that dipole in a uniform electric field becomes PE sine of angle theta. On writing this equation in the vector form, it becomes tau is equal to P cross E. This is the vector form of this particular formula. This is the equation that we got for the torque experienced by the dipole in a uniform electric field. Now we are going to use this particular equation in order to analyze the various cases that the dipole is going to encounter while rotating in a uniform electric field. The first case is when the dipole is along the direction of the electric field, and on being so, the angle between them is 0 degree. Hence, theta becomes 0. Sine 0 is 0. Therefore, the torque tau becomes 0. The dipole aligns itself in this way with the electric field. The second case is when the angle between the dipole and the electric field is 90 degree, which is in this case. Hence, the angle between them becomes 90 degree. So, sine 90 is 1. Therefore, tau becomes PE. The third case is the one where the dipole is on the opposite direction to the electric field. And when the dipole is on the opposite direction to the electric field, the angle between them becomes 180 degree. Hence, putting this 180 in this equation, sine 180 degree is 0. Therefore, the torque, even in this particular case where P is opposite to E, is 0. The fourth case is when the angle between P and E is 270 degree. So theta becomes 270 degree. Therefore, torque becomes minus of PE. Out of these 4 cases, we have 2 such cases where the dipole is unstable and 2 cases where the dipole is stable. In this case, tau is 0. No torque is acting in the dipole. Therefore, it is stable. And also in this case, tau is 0. No torque is acting on the dipole. Therefore, it is stable. Whereas in this case, where P is perpendicular to E, out here tau is PE. Therefore, in this case, it is not stable. And in this case, when theta is 270 degree, tau is minus PE. This is also the case where the dipole is not stable. Taking this particular case into consideration again, out here, this case is the stable case because out here there is no torque acting on the dipole. This is stable. Now there is one more term associated with this is the stable equilibrium. Stable equilibrium. In this case, if I place the dipole in this way, this is the positive side, so this is the negative side, and this is the negative side, this was the positive side. Hence, in this case, there is no way that this is going to rotate. This will be as it is for a longer period of time. This case is known as stable equilibrium. Whereas out here, this is stable but not for a longer period of time, which means the positive is on this side, whereas this was the positive side. This is the negative side and this side is the negative side. So this dipole is always going to have a tendency to rotate. Hence, this type of case is unstable equilibrium. Hence, this type of cases is the unstable equilibrium case, whereas this type of case is the stable equilibrium case, where the dipole is going to be in its stable position for a longer period of time, where in this particular case, the dipole is going to be stable, but not for a longer period of time. So these are the cases when the dipole is placed in a uniform electric field.